So we're going to look at solutions again in mixtures, and also how to separate those. A couple different techniques for separating mixtures. And I guess lastly we'll also look at solubility, how well or how not well something dissolves in something else. So this section has a little bit of vocabulary for sure. Unsaturated, saturated, and supersaturated just describes how much solute you can dissolve in a solvent. Unsaturated means you could put more solute in and it would still dissolve. Saturated is the maximum amount, and then supersaturated is a unique situation where with the addition of maybe heating the solution, you can get actually more solute to dissolve than would normally be possible. Typical kind of questions you would be able to be asked on or have to answer on a test would be things that are very specific, or sometimes not as specific. These are not very specific here. Which of the following is true or are true? Can a gas dissolve in a liquid? Yes, it can. So we can definitely put things like, in a body of water, North Park Lake, for example, there are fish that survive in there, and they need oxygen that's dissolved in the water to survive. So that's definitely possible. Can a liquid dissolve in a liquid? Oh, yes, it can. So maybe ethanol dissolved in water would be an example of that. Can a solid dissolve in liquid? I think that's the most common one that you might have in your head, like maybe NaCl. You have salt water. Salt can dissolve in water. And then can a solid dissolve in water? I'm sorry, can a solid dissolve in a solid? Kind of, yes. So how we're going to kind of get around that to make it a true statement is that if you would take two solid metals, melt them, they would mix, and then let them re-solidify. That would be an example of, I think, what we're trying to talk about here, a solid dissolving in a solid. Okay, so we talked about solutes, we talked about solvents. Let me talk about this for a second. Like dissolves like. We're going to use that to kind of go a little bit further. That's the idea you might have in the back of your head, but I do not want you to use that on a test to explain why one chemical dissolves in another chemical. We're going to go a lot more in detail, and so this is not going to be specific enough. This will not be able to get you into the category of correct answer. It's not wrong, but it just doesn't give us enough information. So we're going to have to go into some details about the intermolecular forces, the Coulombic attractions that those materials would be able to possess, whatever those two materials are. Another vocab, if you have two liquids that create a solution, we're going to call that miscible, as opposed to two liquids that don't create a solution. That's going to be called immiscible. So what would allow something to actually dissolve or not dissolve? So there is a solvent-solvent interaction. Let's look at it as a solvent. I think our universal solvent would be water. And I'm drawing two water molecules here. So that solvent-solvent interaction is that right there, that hydrogen bond or hydrogen bonding that occurs between water and water. It's a pretty strong solvent-solvent interaction. You might have a solute-solute interaction, like maybe Na. I'm going to put it with the dotted line there, but I think we've kind of represented that earlier as a lattice structure, but that's going to repeat. But that would be, we'll kind of do that. Okay, so that is a solute-solute interaction. Then, if you would allow those two things together, not everything does this, but NAs and CLs with water will do this, is you'll get a solute-solvent interaction. And we've drawn this now a few times. Sodium ions, any cation would be attracted to the oxygen part of water, and then chloride ions would be attracted to the hydrogen part of water. So that's a solute-solvent interaction. So all those things are taking place. And what really has to happen here? Let's go another Keller. So for a solution to develop, you would have to break that hydrogen bond between water molecules. You'd have to break the coulombic attraction between Na plus and Cl minus, and then you would have to, so let's use some words here, break, and then this one is form. You would form these interactions. So when you break bonds, energy is absorbed, and when you form bonds, energy is released. So all those things are going to have to interplay for a solution to develop. If one of these things can't be overcome for some reason, then it doesn't occur. The solution doesn't occur. So again, I mentioned that maybe as a starting point we can use this term like dissolves like, but we're not going to use that to actually get into the details for answering a question correctly. Let's back up a second actually. So we do have an interaction here, the solute-solvent interaction. So the like and like, they're both charged particles, the Na plus and the water, the oxygen part of water, or Cl minus with the hydrogen partial. I should put a little parentheses there, which I did not for water. Okay, so that's where the like and like comes in. But what we're going to talk about is that water is a polar molecule with strong partial charges, and ionic compounds like Na plus and Cl minus, they're ions obviously, and there's a strong coulombic attraction between those two items, as opposed to like versus like. Okay, so we already discussed the ionic salt in water. So that's an ionic dipole interaction, and we already described that. But how do you get nonpolar molecules to dissolve in each other? And that happens all the time. There's an LD attractive force there. So if you would try to take a nonpolar substance though that only has LD forces, and you would dump it into maybe a beaker of water, you would not get a solution, because the water, it has more coulombic attraction to water than it does to the nonpolar other material that you dumped in there. So those things would never like to mix then. Oops. Okay, so a couple questions here. Pick the best solvent. So if we had bromine gas, you have to know, so we're going to have to look at these compounds. Bromine is a nonpolar molecule. So nonpolar molecules are not going to have any coulombic attraction to water for example, because water is a polar molecule. Water would have more Coulombic attraction to water. So if you wanted to dissolve bromine Br2, I guess typically it's a liquid at room temperature, but that's not important. You would have to use something that's nonpolar, and benzene is nonpolar. What kind of forces would occur there? They would be LD forces that would allow these two things to interact and become a solution. KCl is ionic. Ionic would have a strong Coulombic attraction to things that are polar. Carbon tetrachloride is nonpolar. So, by the way, let's kind of X out the things we don't like and circle the things we do like. Ammonia is a polar molecule. So it would have a strong ionic dipole connection there. Methanol, that all means, here's the compound methanol. I didn't put all the H's in there, but it ends in this OH alcohol group, and that's going to give it specific, it's going to be a very polar molecule in that spot. So mineral oil, that's going to be nonpolar. That's not going to work out very well. No Coulombic attraction there. But water, obviously very polar, so it's going to have a strong interaction between other things that are very polar, like methanol. Oh, so you'd think octanol would have the same idea, except octanol has, so let's put these H's in here. Let's finish that. 3, 4, 5, 6, 7, 8, if I didn't lose count there. And at the very end has that OH part. Well, guess what? This whole part of the molecule, all these H's here, that's a lot of H's. This is primarily a non-polar molecule. Just has that teeny little bit of OH minus, sorry, not OH minus, but the O that has the partial negative charge and the hydrogen has the partial positive charge. So it does have a little bit of polar nature to it, but the majority of the molecule, the vast majority of the molecule is nonpolar. So if you actually dumped octanol into mineral oil and water, there's probably not going to be enough OH to give it Coulombic attraction to water. It turns out that the LD forces there are going to allow it to dissolve in the mineral oil much better. Most alcohols actually are going to be more nonpolar than they will be polar. If you have methanol, if you have ethanol, if you have propyl, those dissolve well in water, but then once you get past that, they don't dissolve very well in water, or at all. Okay, so factors that affect solubility. So we've already mentioned the type of compound it is. That has a huge importance. The temperatures, so if you have a high temperature, you'll be able to dissolve most things easier, except for gases. Gases, it's the other way around. So if you have low temperature, the gas will dissolve better. If you have a high temperature, the gas comes out of solution. Agitation, stirring it up a little bit, that helps. Surface area, so if you ground your sugar into powder, it might dissolve better than if you have a big chunk of sugar. And then also unique to gases, pressure. If you try to dissolve carbon dioxide, for example, under high pressure, it will dissolve better. So if you have a can of Pepsi, it's under high pressure. That CO2 that's in there, all those bubbles, if you pop the can and pour it into a glass, you'll see all those bubbles of carbon dioxide. They're coming out of solution because now you don't have that high pressure, you have a much lower pressure situation. If you wanted to separate these mixtures or separate solutions, there's a whole bunch of ways. We're going to just touch upon a couple. Distilling. You would use different boiling points. Things boil at different temperatures. So something boils off first, something boils off second. If you can capture that vapor and maybe condense it back to a liquid, that would be distillation. Chromatography. You can use all kinds of different chromatographies. We're going to talk about mostly paper chromatography, but with any of these chromatographies, you're going to have two situations. You're going to have something that doesn't move and then something else that moves. And you're going to have a solute and a solvent. And depending on how well the solute is attracted to something, that's going to determine how far or how not far it goes. And I'm going to show you what that would look like in the next slide here. By the way, we have also filtration. You could also use a centrifuge. And a centrifuge is nothing more than a high-powered, spinny type of apparatus. For instance, if you were working with blood is a mixture. It has some things that are heavier than other things, more dense. And if you would spin that, the heavy things would go to the bottom, and then the light things would go to the top. And you can separate the red blood cells from the white blood cells and platelets and the plasma using that method, centrifugation. Here is chromatography. So with chromatography, you would start with, I think this is paper, and you would put a little dot of a mixture there. And then you would add a solvent. And the solvent will start to go up and up and up on this piece of paper. And as it touches that original mixture, if that original mixture has parts of the mixture that are attracted to the solvent will carry it away. If the parts of the original mixture are more attracted to the paper, it'll not travel as far. So you can, over a period of time, separate out the two components, in this case, two components of this mixture. So it looks like this is like about half, a little more than half done. And then someone stopped there, and you can see that these two items separated from the original mixture. And now we can figure out which one's which. So let's see here. Polar, nonpolar, I'm reading the stuff on the left here. Polar, nonpolar solvents carry the solute along the column. Does it tell you? It actually doesn't tell you what type of solvent we're using, but we have answers here so we can determine what type of solvent it was. So the solvent had to be a nonpolar solvent. Why? Because the less polar item went further. It was more attracted to the solvent and less attracted to the, we don't even know if this was paper, whatever this material was. But this material, we'll call it thin layer, that had to be polar. So component A was more attracted to the paper thin layer than it was to the solvent. Okay, so here's a typical question. So it looks like here, this is a nonpolar solvent, and it's going to draw up the container, or not the container, the paper. And we have this time 3 different dyes that are mixtures. Well, they might, I guess in this case, they're not mixtures. This is a mixture of possibly A or B or C. We're not really sure. It says unknown. So we do some knowns against an unknown, and the solvent's going to draw that up. If the solvent is attracted more to the dye is going to travel. If the dye is more attracted to the paper, it won't travel. So over a period of time here, looks like this is where these three ended up, and here's where the solvent ended up. So the unknown looked like it went about halfway. Which of these dyes went halfway? So I think by that alone, we can tell that the unknown is A. We haven't described anything else about it. Because C went the furthest, it's most attracted to the solvent. And the solvent was non-polar. So that means C is the most non-polar. That would mean dye B is the most polar. And that would also mean that this paper must have the most polar quality. So I think we probably answered all the questions that are being asked there. Okay, a little more on the vocab. Electrolytes, how well they break up into ions. You have ionic compounds that break up into ions very well, strong electrolytes. Weak electrolytes are going to be weak acids. Weak acids don't completely break up between the H and whatever else is there. So that's why we give that a double arrow. And then lots of things still dissolve, but are not ionic. So they dissolve. AQ means aqueous, dissolved in water, but they're not going to have any ions. So they're not going to be able to conduct electricity. A few more vocabs here. Colloids, Tyndall effect, hydrophilic, hydrophobic. Colloids are tiny, 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 tiny little particles suspended in another material, and they're so small that they don't fall out of that suspension. Fog, terrific example. Whipping cream, milk. Those would be all good examples. And how do you know if you have a colloid or not? If you take a flashlight and you try to pass the light through the material, and the material, the true colloid, takes that light and moves it in different directions, scatters it, and maybe even the light comes back and hits you like fog. If you put your high beams on, that high beam light will come right back at you, kind of blind you a little bit. That would be the Tyndall effect. That's all for today.